And there's the red light. Okay, Glass, Facts and Fallacies. I like this book because it's a lot of bite-sized chunks. And frankly, he doesn't wander around as much as DeMarco and Lister do in Peopleware. But boy, there's a lot of stuff to cover here. Okay. And a lot of this stuff, some of this stuff I'm going to rip through pretty quick because we've covered it before. And of course, you're supposed to have read this. Section 1 is on management people. The most important factor in software work is the people. I can't say that often enough. If you can have, in fact, as I put there, you can have a bad methodology and a bad technology base, and you have great people, and they will do great work. You can have the best methodology, you can have all the latest tools, you can have high-end workstations, and if you have poor developers, they'll produce crap. That's the simple truth. Most of you have not seen the bad code that I have seen. And in many cases, this is bad code commercially available. When I was hired by Apple as a contract programmer back in fall of '88, they had licensed the source code for a multimedia package that ran on the Macintosh. And Apple wanted to use this both use this to develop both user tutorials. So if you bought a Macintosh, you got a user tutorial that would teach you how to use the machine, and for self-running demos and dealer things. This was by a well-known, in the Macintosh market in 1988, well-known software company. It was written in Pascal, which at that time was my favorite programming language. And I was appalled at how absolutely wretched the source code was. There was one routine in particular where they wanted me to A, fix bugs, B, add new features, mostly special graphics effects. And there was one core routine that for starters was probably about 400 lines long. A subroutine. Had about 20 go-to statements in it. And it would jump ahead and go, and then it would jump back, and then it would go away, and then it would jump ahead, and then it would go back. And I spent about a week trying to figure out what this thing was doing, so I could fix it. And finally, I threw it away. I didn't throw it away completely, but basically, I replaced it entirely. I analyzed it, figured out what it was doing, and I rewrote from scratch a routine that was about half the size, did not have a single go-to statement in it, and that did everything that the routine did, but without the bugs. And then I started adding features. My very first job out of college was at General Dynamics in San Diego, and I remember there seeing a Fortran subroutine that was really only about 50 lines of code, but that had 10 go-to statements in it. Again, jumping back and forth. No flow of control, no structure. You will be amazed when you encounter it at how bad some working code out there is. There are a lot of people working in industry who shouldn't be working in industry, who produce wretched code. Well, it's about time. Just kidding. Anyway, so why is this issue hard? Because it's hard to find and hire great programmers. I have seen situations. I was asked by one company several years ago, they were they had a full-time consultant in place who was a great programmer, but the company wanted to replace him and actually hire somebody. And they came to me because of contacts and said, can you evaluate, in particular, these two candidates? And I talked to them, and they talked a good game, and the resumes looked good, but I said, I told the company, I really can't recommend either one. I said, if you could somehow merge both of them into one person, that might be a useful person. So our decision was they hired them both. And it was a disaster. It's like, no, the issue wasn't that the two of them together can do it. It's that both of them lack certain things to prevent them from being great. Yes?
What were the things that they didn't have?
I would ask them certain questions, pose problems to them. And it's kind of like they would start tap dancing. There's a difference when you're talking to someone, and again, this wasn't your Google, how many phone books are there in the city of Chicago type puzzle question. It was kind of like, okay, here's a typical problem, or here's an issue. How would you start to address this, to do the analysis? And they would start talking, and they would say a few right things, and then it was kind of like the water was about an inch deep. Yeah, they would give some superficial answers, and what I would look for is someone to say, okay, let me tell you about the problems. You haven't given me enough information yet to address. I'm going to have to do this. I'm going to have to do this. I'm going to have to do this. That's going to require that I know this much about this much about the background, this much about the problem, and you haven't given me that information. Therefore, I can't give you a complete answer. That to me is someone I'd say, okay, this is someone who immediately sees the implications of what I'm asking in terms of what information they don't have. Best programmers. Okay, you've got anywhere from 5 to 1 to 28 to 1 differences in productivity. I've known some programmers who are just incredibly productive, and they produce clean code and it's bug-free. I have known other programmers who don't work that fast, but frankly, they produce good, solid code that's well designed. The variation is fine. Not everyone in a symphony orchestra is going to get up and do a solo. But as long as they can read the music and can play to the standards of the orchestra, that's fine. Same thing is true in software. There are cases where, and as I've said repeatedly, you don't want too many geniuses because they'll spend their time all arguing with each other as to what the best solution is.
And constantly come up with better and better solutions, but not produce any code.
I'm sorry?
And constantly come up with better and better solutions, but no code will be written.
Oh yeah, well there is that issue too. That's another thing. Again, Steve Jobs, real artists ship. Okay? I don't agree with everything Steve said. It's certainly not a lot that he did. He had a rather abusive management style. He recognized the fact that you have to ship. And so you have to make those hard decisions and say, here's what this is. At this rate, we're never going to get through this. Okay. So the goal should be to find, hire, and keep the best programmers. Instead, we often drive them away. This is the Dead Sea effect. You hire great programmers, you do a poor job of management, you create an environment that is counterproductive and often just downright stupid, and all your best people leave. Adding people to a late project makes it later. We've talked about this before. It works. In fact, he cites people where the working environment has a profound impact on productivity and product quality, and organizations just don't get that. Oh, they'll be out and out, we'll have spontaneous creation, and people will interact, and we'll have new things that, most of what you do as a programmer. I mean, yes, you want to interact, but most of what you want to do is get into the flow state and not have anyone bother you at all and produce. And as per the comment with the outside distraction, you made it, about the distraction of projects, someone over here did. Okay, that's right. It's hard to context switch. It's hard to be working on 3 different, my rule of thumb as a CS undergrad was never take 3 or more coding classes in a semester if I could avoid it. 3 was the absolute maximum. For exactly that reason. It's the context switching. And yet companies will focus on, it's actually a lot cheaper and more flexible. We'll just put a bunch of tables out. And we can just, change it as our population fluxes, fluxes and varies and so on. Tools. Hype is the plague on the house of software. Okay, now we're back to the silver bullet syndrome. And people keep claiming some new tool or methodology or technique or approach or language is going to give an order of magnitude that is a tenfold improvement. And almost all of them turn out to be somewhere from 5 to maybe 35% as far as improvement goes. And I've been watching this for 40 years. Again, as I've said before, I wrote a book called Pitfalls of Object-Oriented Development. And I was after several years of professional object-oriented software development. Specifically, say, here are all the mistakes people make. And a lot of it is believing their own hype. So any claims for tools or methodologies that are going to revolutionize programming, just, keep a tight grip on your wallet. This is so important. Lowering a new tool or technique, methodology, whatever, lowers programmer productivity and quality initially. In other words, if I'm switching, and again, this has come up, some of the discussions, it's kind of like, okay, I'm really used to using Java under Android, and suddenly I'm trying to use Swift under iOS, and I think I'm going to be as productive. No, you're not. There's a lot you can bring over, and you're going to see the parallels and so on, but you're just not going to be as productive. And the irony is how often a company will switch to a new tool, a new environment, a new methodology, thinking it will bring immediate increases in productivity. It will shorten schedules instead of just the opposite. It's going to slow things down.
I just wanted to say, this goes more with the last slide, is that the best programmer that I know personally works in Notepad++, which I think is so horrendous. But it's not the tools that make the programmer. No, it's not. And that's actually a very good point. And there are a lot of great programmers who, if I were to come out and say, I've got this great improvement on software engineering. Let's do everything in C using structured development. And people would say, whoa, those are both ancient technologies. I said, yeah, but a lot of great software was written using that. It really does boil down to the people that you've got. Software developers talk a lot about tools, and here he's talking about external tools beyond simply, whatever compiler or interpreter you're using. They evaluate quite a few, buy a fair number, that's number, not numbers, and use practically none. And this is a question outside of whatever your current favorite IDE is, how many software tools do you use? Of course, you're all using, Git here, yeah. And that's something interesting to note. There are certain tools that will establish themselves over time. Now, but what I find most interesting is that at Pages, so we're 1990, so we're talking about 27 years ago, as soon as we hired our third programmer, we set up SCCS. This is all in the next step, so it's all Unix, so we had SCCS built in. Source code control system. So we started doing a source code repository. 3 programmers sitting in the same open office, and so on. The multi-million-dollar SAP project that had people scattered, programmers scattered all around the world, this is the one I testified on back in June in New York, never had a source code control system at all. They used email. Mail around source code. And I testified about this on the stand. I said, this is professional malpractice. I said, you can get great source code control tools for free. There is no excuse for any kind of project beyond 2 people not to have a source code control system. So the profiling. How many of you are doing profiling currently with any of your projects? Good. Profiling tools can be great. I highly recommend them. We often don't think about those until we're deep into testing and trying to figure out why our product can't, complete what it's supposed to do on time. It's like, oh, look, there's this bottleneck right here. Now I have to rewrite that. Anyway. And actually, I have a question here.
what have you learned about certain tools so far in the course of your projects? A lot of you have had to adopt tools that you've never used before. What's been your reaction, Betsy?
Well, one thing is a tool which you think you're familiar with can have many aspects that you don't actually know about when you start talking with other people.
Yes, yes it can, including many pitfalls, right?
Going to what you said about ones that are more established, I think like the tool in itself isn't as important as if the community has embraced it, because if you have a tool that's just widely used, there's more documentation, there's more forums, like that to me is more important than, you could have the most important tool or the best tool, but if no one really knows how to use it, it becomes worthless because you hit all these dead ends that no one else has
There's
figured
nothing
out.
on Stack Overflow.
Yeah, exactly.
I use Stack Overflow. Any other thoughts? I think someone else, it may have been last week, someone was talking about the fact that they found that the engineer, and this may be the side scroll, but the engineer using actually behaves differently on different platforms. And it isn't quite as portable as it seemed to present itself to be. False advertising, oh yeah. Yeah, be aware of that. Okay, we've talked about this some. One of the two most common causes of runaway projects is poor estimation. The other is unstable requirements, which we'll talk about. Why is software hard to estimate? We keep going back to armor. The more different the project we're doing is from something that has been done before, the more discovery and invention is required, and less likely we are to know how long it's going to take or what dead ends we're going to go down to. I mean, frankly, you guys, with tackling blockchain is a classic example. It's kind of like, okay, we're going to do this, and we don't know if we're going to, be able to get through everything we need and figure out what we need to know. There are reasons why estimation is poor, and we're going to talk about that. But as per our discussion was last week on metrics, there's been a lot of time and effort spent on project estimation models. You've got Kokomo 2, you've got stuff Capers-Jones has done, SPR. You've got a number of models, and they still don't work all that well, because we often just don't know enough about the eventual solution for a project to build that in to the estimation. And of course, above and beyond that, you have this last point, which is often you'll run across a project where the engineers are saying, no, there's no way we can do that. We already know this is unrealistic. But, and that's going to be a specific issue we're talking about in a minute here, management says, oh no, we have to have it done by then. Okay, most software estimates are performed at the beginning of the life cycle, except that often before requirements are fully defined and thus the problem is fully understood. Estimation therefore usually occurs at the wrong time. Okay, here's the problem. If you don't know what the time and cost is for the solutions you're going to have to come up for the project, you really have no way of estimating. Your ability to estimate increases with the degree to which you understand the problem, but as Armour points out, if you're simply building the same program over again, what's the point? I can tell you where the point works. I talked to a company, oh my gosh, this is probably mid-90s, whose specialty was software to run power utility plants. They had existing software, and they had a very rigid process where they would go in, and for a fixed fee, they would analyze the needs of the particular utility plant. They'd come up with like a 200-page screen-by-screen document. Say, here's the screen in our software, here are the changes which you said you need. And the customer would have to sign off on that, and then this company would give them a fixed price bid. And they had developers all over the world who knew the software, and all they were doing were modifying the aspects of the software according to this 200-page document. And they could successfully do fixed price projects time and again because they were basically re-implementing the same software over and over again. All they were doing was modifying screens and putting different business logic in behind it. Most software isn't like that. Okay, most software estimates are made either by upper management or by marketing, not by the people who build the software or their managers. Estimation, therefore, is done by the wrong people. You will find this. It's a bit like, as I say, it's a bit like management or marketing deciding how long it should take to build a dam or a skyscraper without asking the architects and civil engineers. Now, no one would do that, one would hope. But it's what happens with software all the time. And our own contribution, we have to stifle our optimism. Yeah, if I work a few nights, I can get that done. And on the management side, the unwillingness to give bad news upwards. Software estimates are rarely adjusted as the project proceeds, thus those estimates that are done at the wrong time by the wrong people are usually not corrected. Now the pattern that I've talked about, which I've seen over and over again, is that's true until like 3 weeks before deadline. At which point everyone realizes, oh, this is wrong. And then whenever they slip the project, it's usually not far enough. It's kind of like, oh, well, like I said, it's a little eerie how often I run across this 3 weeks before and we're going to slip it 6 months. And that goes on time and again. Which, going to Brooks, if you're ever in a position where you have to slip a project schedule, take what you think it's going to take and double it. Because that's probably more accurate. As sad as that may be. It's often very hard to do, but it's more accurate. Again, one of the painful lessons at Pages was this year that we were late. We didn't slip it a year. We typically slipped it about 2 or 3 months at a time. And part of the professional agony for me was going back in front of the investors and giving our new estimate as to when we were going to ship and having them say, why should we believe you? You've been wrong every single time up till now. And I had no good answer for that. Other than I basically swore a vow I'd never put myself in that position again. Okay, since estimates are so faulty, then we shouldn't worry about them. But everyone's concerned anyway. Why do we manage by schedule? Yeah.
For one thing, it helps put a sense of urgency and direction. I mean, if you say we need to have a prototype in 2 weeks, you're not going to spend all the time doing all the little side projects. You're just going to get it done. Whereas if you say, oh, you've got time, just whenever you're ready.
Okay, that's actually very good, and that's very important. A time box is what we're doing. Why else? Why else do we manage by schedule?
It's how businesses think.
It is how businesses think, and it's often essential for businesses. It's like, okay, we have to figure out where our revenue is going to come from in 2018. Therefore, we need to know what products we're going to have to sell and where we're going to have to sell them, and what features they're going to have, and how they're going to stack up in the market against all our competitors' products. There are reasons to manage the schedule. The problem is that this is often put down on a software project without recognizing that if you're going to fix the schedule, you have to be flexible on features. That's the trade-off. Okay, if we have to ship by June 15th of next year, then we have to be willing to keep throwing out features as we go along. And business will come back and say, but it won't sell. Well, that's, I would like to argue that, we can somehow bend reality, but in some cases you can't.
So after reading all of these, it just got me curious, like in your experience, have you seen a project that like grossly overestimated on purpose and then finished super early? I mean, from this it sounds like that's impossible.
Oh, actually it is possible. Yes.
It's rare, I'm sure.
I have seen development teams, and this is why you sometimes run across these rules of thumb that say things like, take your best estimate, double it, and add 10%. And that's what you tell management. And I've run across teams that basically have taken that approach, have pushed back against any effort to shorten the schedule, and they deliver on time and under budget. There are organizations that do deliver on time and under budget, and it's usually because they are very, very conservative in the sense of giving themselves a lot more time for their schedule. But you have to have management that's willing to trust you and recognize, there are no miracles in software. In fact, I mentioned this in one of the earlier lectures, there is a danger. There was one large financial company whose name you'd recognize that had a project to completely revamp their customer-facing credit card website. And against all odds and expectations, they actually delivered on time. But they did so with a lot of, duct tape and baling wire and so on, saying, okay, now, we got this up and running and we're sort of holding it together, but now we need to take time to clean things up behind. Technical debt is what it's usually called. And instead, management said, great, let's do it again. We want to do version 2.0 in 6 months and add all these features. And the developers' heads were exploding. It's like, no, you don't understand. This was a miracle this happened at all. And I was part of a team that was actually brought in because management was saying, well, why are they having such trouble? And we came back and said, well, here's why they're having such trouble. They did a miraculous stunt to pull off, meaning is you need to give them the time and space to clean it up. Back off on your upgrade plans. Let them go through and make changes. And in one of those rare instances, they actually listened to us and gave them time and space to do some cleaning up and slowed down their plan feature stuff. Okay. There's often a disconnect between management and their programmers. Yeah, duh. Though this is an interesting one. This is one where he talks particularly about a project that was way over budget, way over schedule, but when he asked the developer says, oh, it was great. And they said it was great because they didn't care about the budget or schedule. They actually got the program working. It was very high quality, very highly reliable, and they solved some interesting problems. So their concern was not the schedule or the budget. It was simply, by golly, we wrote good, solid code, and it solved some interesting problems, and it works, and it's out there. Interesting. Projects where no estimates were prepared fared the best in productivity. This is sort of counterintuitive to the let's put the pressure on. But productivity is this gets back to the story I told like the first day of class, maybe the second day, about the wood carver who said, I never finish these doors, they come and take them away from me. And a lot of the current movement towards DevOps, I don't know how many of you are familiar with DevOps. Basically, it's sort of a continuous, it's like Agile, but Agile across also operations and the whole company. And the idea, it's what, say, Facebook does. Facebook programmers can make changes and check them in the same day. And that's why, for those of you who've actually used Facebook, you'll be working, it's like, where did this come from? This has this new feature. And it's just going, constant changes. Occasionally they make mistakes. And you go to Facebook and it's like, stuff is broken all over. Some developer checked something in without proper testing. The idea is to have continual changes made to the software. Multiple changes made a day. With a lot of automated testing, we're going to talk about automated testing, but a lot of automated testing, a lot of regression testing, and to constantly update it on a regular basis rather than to have big staged, here's we're defining release 2.0 and this is when it's going to come out, here's everything we have to do. Remains to be seen. DevOps is currently touted as a silver bullet, so that sort of gives you an idea right there. I always like this one. The answer to a feasibility study is almost always yes. Now, I don't necessarily agree with it because I've been in situations where I've stood up and said, no, we can't do this. We still don't know what the problem solution is. But you'll find yourselves in situations where if a company says, we want to do X, can we do this? They'll usually find a way to say yes. Smart companies will look at something like that and say, you know, that's interesting, but we're not sure we know enough how to solve the problems. Therefore, we're going to do a little pilot project to explore this, and we're just going to put it on the back shelf or put it on the side for now until we get a report back on the pilot project. Reeves. Now, he spends a fair amount of time on reuse, which was a big issue in the 90s and into the late 2000s. The book was written in 2002. It is less of an issue now because reuse was another one of those silver bullets. We're going to build software components, we're going to put them together, and we're going to have systems that we can construct that are solid and reliable and build very quickly. And it usually doesn't happen. Libraries of subroutines. That basically predates even me. Works just fine. Most of you have used APIs, you've used libraries. A lot of them are bundled with the operating system, obviously. A lot of them are bundled with IDs and so on and so forth. However, this idea of reuse in the large, we're going to build reusable software components that we can plug in, is mostly an unsolved problem. Where does it work? It works in things that are domain specific and that are sort of, for lack of a better word, orthogonal or independent to what you're solving. For example, graphics engines, physics engines. It's like I'm going to build a game on this engine. The engine doesn't incorporate any of the game. It simply provides an environment in which it's like an operating system on top of your operating system. It provides an environment in which I can develop the game. Components like that are useful for reuse. And the idea of sort of building universal objects, that was a big thing in the 90s, and it just failed. I think I may have already mentioned when I was at Fannie Mae as a consultant, I was one of the advisors to their in-house corporate reuse project. They were switching to object-oriented development, and they wanted to develop. Fannie Mae deals with loans. They buy mortgages, basically. They buy mortgages. When they buy them, they manage them. They bundle them to the mortgage-backed securities, put them out on the market, collect money from there so they can buy more mortgages. Fannie Mae is created by the government, basically to buy mortgages from banks so banks would have more money to give out to people wanting mortgages. So, the loan, the actual mortgage. It's like this is a no-brainer. This is what all our systems revolve about, is the concept of a loan. Therefore, we should be able to have a universal loan object. And I watched them work on this for a year and finally abandoned it. Because while they had many different systems that used loans, each system's abstraction of a loan object was different. And you were ending up with this massive blob-like thing. I mean, it had a couple hundred fields, it had hundreds of methods, and any given application was only using a small subset of both the fields and the methods. That sort of summarizes where reuse went. Building a reusable software component is tough because there's fundamental paradox here, which is the more general it is, and therefore the more able to be reused, the less suited it is to any given application. So if I build a general object that represents a student, then my student object for teaching a class is going to be different from a student object for the health center, which may be different from a student object for the administration. And you can see how you start to glom on completely different sets of information, all as a student. Whereas actually, those are 3 different kinds of students. I mean, they can all be you, but there's a whole lot the health center cares about that I don't care about. And there's a whole lot that the administration cares about that I don't care about. There's a lot the administration cares about that the health center doesn't care about. Anyway, design patterns. We're still relatively new when he wrote the book. Gang of Four came out with the first design pattern book in 94, 95. And those are sort of just become part of the fabric now of software engineering. Complexity. We're about halfway through. In fact, yeah, we'll go till 10 till we'll take a break. Let you all wake up. Number 21 is important. This is based on actual research. This isn't a rule of thumb. This is a study that Glass tracked down. And we'll actually talk about some of the reasons why this is. For every 25% increase in you've got a problem that you've defined that you want to solve. For every 25% increase in the complexity of that problem, there's a 100% increase in the complexity of the software to solve that problem. It's a multiplier. It's not one-to-one. And this is why the unknowns are so deadly. Because you get into a project and stop and think about the projects you're working on just for this class. Stop and think about some of the things that you have encountered in your respective projects. It's like, oh, didn't realize we're going to have to deal with that. And what you see as that impact it's having in the solution you're writing. Now sometimes these are nitpicky problems. Oh, we have to be able to go and get this data. Here's how to do it. But when a core problem itself increases in complexity, the software increases fourfold in complexity. This is why estimation is so often poor. And this is why we get back to the diagram from Armour, why some of the false areas that we get into and the things we discover turn out to expand greatly the scope of what we're working on. 22, 80% of software work is intellectual. Again, he's basing this on studies that have actually observed people working, doing software design and development. Most of the work is intellectual, and a fair amount of that is creative. It's like, I'm looking at all these problems. How can I solve this? We're going to talk about it in a second. A lot of it's mental. A lot of it is you're sitting there running through possible solutions in your head and accepting and rejecting them. And this is, in my opinion, why all the efforts to completely automate software development have always failed. Automation deals with it's kind of like component software. It's kind of like, oh, we're going to assemble these components together and just, invoke these methods and everything will work. And that sort of gets you to your base level of functionality, but it doesn't solve the creative and intellectual issues of software. Let's take a break now. Break till 3. Whenever everyone gets in, let's see. Okay, break till 3 or whenever everyone comes back. Whichever is sooner. Walk around. Wake up. It's that rough part of the semester.
Yeah. The post-midterm blues is the word.
Yeah. There's a reason I delayed the midterm, and there's a reason why you don't have any assignments the week of Thanksgiving.
It's the post-midterm thing, because the midterm you're stressed and you're in high alert, and then afterwards you just sort of lull.
You assume that we're done with midterms?
Oh.
2 midterms this week.
Our midterms are late. I laughed about the software we use. My dad only coded for a little bit in college, and that's all he really remembers, and that's what he always brings up whenever he talks about coding. So I'm like,
It was a big thing in the 90s. We're going to do reusable software components, software factories.
He was a bit older than the 90s when he was in college.
And it was a lot of the concept was tied to ways into it. I heard that. Okay. Besides poor estimation, unstable requirements. There are two forms of instability. One is failure to adequately capture the requirements in the first place. The other is commonly called scope creep, which is that in the middle of the project, whoever the manager, customer, marketing person is says, oh, we want to add this also. And again, the key to a successful software project is dropping requirements. I can't say that often enough. When I have a successful software project, be prepared to start dropping requirements as you get further along, because you'll buy yourself time and you'll say, oh, well, if we don't have to do that, then we can easily get this and this done. Now, there are problems with the unstable requirements. As he puts here, most projects that spin out of control were never in control in the first place. That is, the requirements were not sufficiently defined and locked down. Now, there are problems locking down requirements. He's going to talk about these in a second. Some of it is the requirements explosion happens when you start actual design and implementation. But a lot of the problem is the temptation of adding new requirements here as well. In other words, you don't realize first everything you're going to have to do to accomplish what you think you're going to do, and then you start adding on to that. We want stuff to work to be able to do this as well in order to be functional. In some cases, for those who end up working in commercial software, it becomes very tough because it's like we have to be competitive, and if we don't have this function, we're not competitive. Have you ever, I mean, how many of you had the experience of grabbing some 1.0 release of an application, a game, an app on your phone or tablet or whatever, and you say, oh, that's lame, there's a lot of stuff it doesn't do. Okay? The reason is because they wanted to ship it. And they said, okay, we're going to defer, just like you defer bugs, you defer features. Kind of like, okay, this feature is getting moved out of 1.0 into 1.1 or 1.5 or 2.0 or whatever. Any other problems with the users? A phrase which I have run into in multiple situations. We want it to work just like the old system, but better. There is a real challenge, and this is going to be true for those of you who end up working on, say, corporate systems that end users within the corporation want, where you're re-engineering or replacing a legacy system. The pushback from the users and the need for change management, basically letting the users know, yeah, this is going to be painful, but you're going to have to do things a different way. It's a big problem. I have seen software projects founder on this, like an iceberg, where the users were so resistant to the changes required in their behavior and what they had to do by the new system that they simply refused to use it and demanded to stay on the old system. People hate change. There used to be this whole theory of requirements traceability. You put all your requirements in a big table and so on, and then you traced it to the portions of code. And so for each piece of code, as you test it, you could say, yeah, we're doing this requirement, this requirement, this requirement. And the problem that kept cropping up is that the table of requirements kept getting bigger and bigger and bigger, and it was requiring a lot of time and effort to continue to try and trace the requirements into specific portions of software. Now, requirements efforts are the most expensive to fix when found during production, but cheapest fix during development. I've told multiple times the story about Larry and the rotatable headlines. Okay? If I had known, while I was doing the architecture for Pages, that we had to have rotatable headlines, then we could have planned for that. We could have put it in the architecture, in the design requirements, said, okay, we're going to have to deal with this and be able to do this. It came when we were like just a few months away from shipping. It's like, Larry, no, you don't understand. It would be, it's kind of like we've just built a skyscraper and now you want a underground swimming pool 3 stories down. It's like the foundation is in place. It's going to be very expensive to go in there and try to mess with foundation and
redig this and so on. The problem with this, and this is why software is hard. Let me say that. Software is hard. Because you get stuff like this. You find out requirements are not there. You've got the system, it's shipping or in production, and you're trying to figure out how to go back and add those. And it's messy, and it's ugly, and it's hard to anticipate what all the requirements are. Missing requirements are the hardest requirement errors to correct. That's where the, you know, and I didn't consider the rotating headlines to be missing, but if it turned out it was actually essential for pages to have rotating headlines, that would have been a very expensive error to correct. I think we could have made it work eventually. I'm pretty sure we could have, but it would have been ugly and messy. It would require reworking a lot of the inherent design decisions that were made in how documents were structured and how they were maintained. There was a word there that just went away. Never mind. The problem is if you fail to capture what turn out to be critical requirements, this will cause problems when you get close to or into production and you suddenly have to do significant rework. The problem is sometimes you don't know you're missing it. In other words, the requirement, there was a project, large financial company, I was doing the review, but we had some other people in with the consulting firm I was with, OSG. And one of their problems, they were reworking. They had a legacy system that was mainframe assembly language software that did credit card processing. They bought up a bank, and so they were now a bank themselves. They could do credit cards and so on and so forth. And they had these old mainframes, and of course, the problem they had is that they had to close transactions out, and they were growing rapidly, and it was overwhelming their system. So they'd had this in-house project to, we're going to re-engineer all this, and we're going to use Corba distributed objects and all this cool stuff and so on. And so they had written this distributed object package that took data from the mainframe in EBCDIC, which is the extended decimal binary coded whatever. Basically, it was IBM's equivalent of ASCII. Very popular on mainframes. Took the data, brought it over to a Unix server, and used distributed object technology to convert it, and then could do the processing to close out the transaction and convert it back from ASCII to EBCDIC and move it back. Well, the problem was that the time it took to do all this conversion was 3 orders of magnitude too long. It was 1,000 times too slow. Because they had this big infrastructure and so on. And this was one of the problems we surfaced real quick. Said, this will never work. Literally 1,000 times too slow. And one of our senior architects, Rocky, I forget Rocky's last name, was the one examining this code and just sort of shaking his head. He sat down and wrote a 10-line program in C that did EBCDIC to ASCII conversion that basically sped up the whole process by 2 orders of magnitude. Said, well, at least now you're only 10 times too slow instead of 1,000 times too slow. But you need to go and look at this other stuff because this is a requirement. You have a 2-hour window every night in which to do this processing, and people who have been doing the coding haven't been coding with that in mind. When moving from requirements to design, let me ask you guys, as you have moved from your requirements to trying to design your things, what are the new requirements that you've encountered? It's kind of like, okay, well, you know, the side scroller has to do this. We have to detect a collision. Well, to detect a collision, we have to do this. You know, the engine does this. We have to do this, so on and so forth. Basically, you have a requirement explosion as you move into design and implementation that says, here are the things necessary to implement this one requirement. And it's a requirement of, here's how the software has to work, here's the data, here's how it goes, and so on. This is why requirement traceability can be so hard. Is that when you start to code, it's kind of like, oh my gosh, here are all the things we have to worry about. Here are all the things that have to work. That have to work perfectly, that have to work on time, that have to get done just because we want X. You know, again, with rotatable headlines, the idea sounds simple. Well, it's simple requirement, rotatable headlines. Like, okay, let's talk about everything under the hood that's going to have to change in order to do rotatable headlines, and how that ripples out to the rest of the code. There's seldom one best design solution for a software problem. I like this quote: in a room full of top software designers, if any two of them agree, that's majority. I'm not quite that pessimistic. I find that if you get some good software developers around and you start kicking out design solutions, it's often pretty easy to hone in and say, you know, this actually sounds like a workable solution. We'll understand all this. I mean, again, this is something you guys have had to deal with. For each of your projects, you've had in a very short time to come up with a design, architecture, and say, okay, yeah, we're going to deal with this. Now, part of the problem is figuring out and making sure you all actually understand what the implications of that design architecture are. But you can come up with a mutually agreeable creative solution. The idea here, though, we're getting all the way back to Brooks. You want conceptual unity. You want a design and architecture that is internally consistent and where it's easy for a developer who's trying to implement it to say, okay, I understand the basic architecture and design we're working here, therefore this should be my approach in implementing the design to maintain consistency with that. Design is complex and iterative. The initial design solution will likely be wrong and certainly not optimal. He talks about doing the hard parts first, which again I think is important. And he talks about, and I've described this, you know, Monitor Labs, when I talked about spending 3 weeks with my feet up on the desk staring at the ceiling, doing the Tabasco data thing. And what I was doing is exactly this. I was sitting here thinking, okay, do this approach, oh, they'll have that problem. Okay, when we do this, we'll have that problem. And I wasn't even writing stuff down. I was doing my best to run through as many different designs and sort of gradually honing in on an approach where my criticisms were becoming smaller and smaller of it. This is part of the very intellectual part. With Pages, I actually reached a point where I started doing diagrams. I looked this morning, I know I've got the 3 design documents I did, the sheets on graph paper. I found my Pages, my plastic bin full of all my notebooks and everything from Pages. It wasn't in there, so I've got to figure out where it's stored. But I kept drawing this over and over again. I would do a draft, and then I'd think about it for a couple days, and I'd do another draft, and probably did 10 drafts each on the 3 basic diagrams before I finally came to 3 and said, okay, this is good enough. This captures what I want. And he agrees with me that one of the problems, I have great sympathy and admiration for the extreme programming, agile design approach, but the danger of picking a simple solution and simply developing it based on customer feedback often leads to a suboptimal design. If you haven't taken the time to really think through the full universe of things, you can get stuck on a design that turns out to be suboptimal and have limitations that you didn't see. Coding.
This is an important point in situations where you've got a designer and a coder. It's one of the reasons why I think architects should write code. I really do. Which is the designer, when you're, stop and think about when you're writing programs for yourself. You're thinking about the design, okay, I'm going to have this, it's going to do this, it's going to do this. And you keep sort of breaking the design point down into a level where you say, okay, I know what I'm going to do to implement this. I mean, I haven't coded it, and you know, there's going to be discovery along the way, but I know I can start coding it. So that's what we tend to do individually when we're designing and writing our programs. If you have a designer and a coder, often the designer will bring the design down to a certain level and hand it over to the coder, and the coder looks at it and says, I don't understand this well enough to start coding. This isn't as fully developed as it needs to be. Or occasionally points out it's the other way. The designer goes all the way down into the weeds. And the coder says, okay, you know, I'm going to have to back off here. This is too detailed and it hinders me too much. You know, I'm simply laying bricks in a pattern here. It's not, I'm not able to deal with the overall solution. He has this bizarre one where he says, and this is, I think it's because, like me, he's old and he's writing this 2002. COBOL is a very bad language, but all the others for business data processing are so much worse. I don't think that's an issue most people really care about. Except that, as he puts it, there are 20 billion lines of code of COBOL in production. Actually, he didn't put it that. I looked that up. There are 20 billion lines of COBOL in active production, and over 1 billion new lines of COBOL written each year. That number staggers even me. And that gets back, when we talk next week about entrenchment of technology, that's something important. You're going to find yourselves at some point working in languages that you're like, why is this stuff in this language? And how do I deal with this? You know, I like C a lot. It's one of my earliest programming languages. Actually, not one of my earliest, it's a later one, but later is relative. I've written, I wrote the manuals for Borland for their Turbo C compiler, so I did both the reference manual and the user guide. So there was a time when I had Kernighan and Ritchie and Harbison and Steele pretty much memorized, and knew C syntax intimately. What surprised it, that was back in the 80s. That was 30 years ago. C is still among the top 5 programming languages in use. It fills a need. It has a tremendous code base, and it's there. Be prepared to use languages you never thought you would use. I have used an awful lot over the years. Error removal. Error removal is the most time-consuming phase of the life cycle. Remember, Brooks said it's 50% of the schedule whether you plan for that or not. And I've seen enough failed projects to tell you, yeah, that's pretty much what happens. Glass says 40%. He cites others who say 30%. The problem is management thinks it's 10% or less. That's really the core conceptual break there. Management thinks, oh, we'll bring in half a dozen people towards the end of the project, and they'll spend a few weeks. I mean, again, back. Love and admire Larry, but you know, our first interaction is, can't we just hire some college students for a few weeks to do testing? It's like, no, Larry, that's not quite. It's not going to work for a, production grade desktop publishing system. And to his credit, we did hire a director of quality and did build an actual QA group. But you will find yourselves in places where testing and software quality in general are always second-class citizens in the IT department. It shouldn't be, because it's where so many projects fail. I have said before that most development groups would be improved if they reduce the number of developers and increase the number of QA people they have. There you go. Testing. It's talking about testing logic paths. A lot of automated testing is set up to actually force, you can set up scripts to basically force different logic paths his point is that this is often seen as the only kind of testing you're done. And you start to get diminishing returns and diminishing ability to test all possible logic paths within it. And beyond that, a lot of, he says, and this is, he's citing studies here, 35% of software defects come from missing logic paths. That is, from stuff in the software that is failing to handle a particular condition that crops up. Or from execution of a unique combination of logic paths. This is classic. Okay, you know, this value, this variable got this value, and this variable happened to get this value, and this routine got called, and that's like a 1 in 1,000 or a 1 in a million chance, but the whole thing blows up there. That happens a lot, and one of the reasons it's so hard is because it can be hard to reproduce. You get these unique combinations like, okay, we know it blew up here, but we can't figure out why. And if you didn't happen to capture the data somehow, it's not going to help.
And capture the state of the machine.
Capture the state of the machine.
At some of the projects that I worked on for my work, a lot of the times it's what is inside of your cache of your machine. And most of the time our diagnosis is to clear your cache. But if we could have a really good understanding of what their cache state was, then we might be able to program around it. But as it is, you can't really get someone else's computer's machine cache. They just write an issue.
Yep, yep. And part of the problem is that program state space. We you know, I say billions is conservative. The number of different states, internal states of a program, is literally, it sort of exceeds astronomical. Stop and think. If you have, in a large program, you can have several thousand variables, and those variables can have extremely wide range of values. And suddenly the number of unique combinations of variable values, you know, and then you start to add in time and sequence, and you know, if you have, here's a snapshot, and here's a snapshot a microsecond later, and here's a snapshot a microsecond later. And a lot of software quality assurance comes from trying to bound the state space and say, okay, we have done enough coding to basically know that the program is safe within this space, and now we start looking at the boundaries or edges, saying what happens when we start to exceed this, and where do things fail. But boy, it's hard. It's nearly impossible to do a good job of error removal without tools. Debuggers are commonly used. Coverage analyzers often aren't. Profilers often aren't. There are actually some good development tools out there, but management is kind of like, okay, you know, just run the test cases, and if they all pass, we'll ship. Some aspects of test automation was often seen as a silver bullet. And again, DevOps relies very heavily on test automation. And it's you know, attempts to use lots and lots of tools to basically do regression testing and thoroughly exercise, you know, coverage and so on as you're going through. But you have sort of meta questions here. What should you test for? What is proper behavior? What is proper state? How do you define the universe of acceptable versus unacceptable responses? Who creates the test cases or the test plans? Who reviews them to make sure that they are sufficiently coverage? When defects are reported, how do you prioritize them? How do you decide how severe they are? How do you decide how critical they are to be fixed? How do you make decisions as to whether to defer them or get them fixed immediately? Whom to assign them to? And what feedback is there as far as improving the test process? They say, okay, we're clearly not closing the defects fast enough, therefore we need to do this differently. I'm glad he threw this in because this is a sentimental favorite. One of the best debugging techniques is still sticking code in your source code, usually bracketed with compiler directives so it doesn't compile in. But if you set a debug flag, it gets compiled in, and you stick it in the start of a routine and say, okay, dump out the input variables,
and then later on you have a few statements to say, okay, am I going through this loop? What's here? And then as you're about to exit the program, it's like, okay, dump out these things. It's amazing how effective that can be. As far as simply saying, oh, hey, look, that's not what I expected at all. Look at that set of values that's come in. And that's often easier and faster to set up than formal debugging tools, breakpoints. I mean, I love debuggers, I love breakpoints, I love occasional tests and so on. But often doing a simple dump at the start and the end of a routine with maybe a few checks to see what the flow of control in there is a lot easier to set up and frankly often a lot faster as far as finding things. Inspection. He's again citing a study that's saying rigorous inspection can remove up to 90% of errors before the very first test is done. Why don't we do more code inspections? Well, huh?
Optimism.
Optimism.
I got it.
Yeah, I got it. It's done. It can be embarrassing.
This is a freaking problem of mine, but when you're down the rabbit hole on something, you've been doing a process or a subroutine that goes through a lot of different aspects, it can be kind of hard to inspect it.
Yep.
Hard to get your mind around it.
And it can be hard. You can get people in there who did not take the time to study the code. If you're doing code review, part of the requirement has to be, make sure that people have actually taken the time to review the code that's going to be reviewed. Because it's like, well, why are you doing this? Like, didn't you look at this? It can take a lot of time if people are not prepared. It can be very unproductive. There are some ego things. I like Tom Affinito, back when he was at Taligent, which was an effort to develop a next generation operating system that died. Had big sponsors, IBM, HP, and Apple. This was going to be, in part, Apple's new operating system to replace the original Mac OS, and this project died completely, and that's why Apple went out and bought Next and got Steve Jobs back. They had a rule there was at the end of the day, each developer was supposed to grab another developer and do a 15-minute walkthrough of all the code that they had modified or written that day. This is like a far less painful and intrusive version of pair programming. You're not having to sit with someone all day long. But it's sort of, you have to explain things. I found, and this is my point here, especially at Pages, my single most effective debugging technique, particularly when I was stuck, a lot of times it's like, okay, I know it's here, 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 I'll put in some statements, yeah, that's where it is, I can fix that. When I have a tough bug, I would drag someone into my office and say, I've got this bug in the code I'm writing, or some code, and I can't figure it out. And I would go through and I would start explaining, and I would get about halfway through and I'd say, never mind, I figured it out. It's amazing how effective that is. It's very effective. Because there's so much you tend to sort of become blind to. Because you see it so much that when you have to start explaining to someone, you realize halfway through, oh, yeah, now I see. It's like, okay, go away. I don't want to explain to you the stupid error I made. So, oh, look at that. I did it twice. Rigorous inspection should not replace software tools. Postmortems. This is a lot of what I do, but as an expert witness, and usually a few years after the fact. A lot of organizations will not do a lessons learned review on major projects. They should. Every release, every project, everything that ships or goes into production should take the time, get the people involved while it's also fresh in their minds, and say, okay, what went well? What should we do different next time? What are improvements we can make? What are the lessons we learned? I like his statement here, and that's Glass. The wisdom of the software field is not increasing. My take is there's a tremendous amount of literature. You're reading some of the best books here. I've got more recommended elsewhere in the extra credit readings. There's lots of good stuff online.
There's a lot of captured wisdom. The problem is no one reads it. No one. You know, I felt such satisfaction last semester, first time teaching this, when I went to grade midterms. And everyone did, I mean, everyone passed. I don't think anyone flunked the midterm. And most everyone did quite well. And literally, I remember going through and grading midterms and saying, my work here is done. You know, these students understand these problems. They know where to look to where the things are. I mean, that's really my focus here. Is that when you encounter these out in your careers, you're going to say, oh my gosh, didn't we talk about that in class? Or isn't that something out of DeMarco and Lister? And you look and you say, oh, gall, and this is what's going to happen as a result. And then you have the information in your first course is to try and correct it, and if you can't correct it, then it's kind of like, okay, I have to decide how long I'm going to stay here. So, and sometimes that's the decision. It's kind of like, you know, sometimes you just need the job and you grit your teeth and you get through it. But if you see that the company is auguring in, it's like the one I told you about where I laid myself off rather than lay off the guy I just hired. And I told him, go find another job. Because this company's not going to be around for long. They're the plane's going in and not in the controlled landing. You want to have that level of understanding. But this is, again, if you're in a position to do it on projects you're working on, suggest a postmortem. And after the fact, a post-ship review. To capture lessons learned and figure out how to do things better the next time. Peer reviews are both technical and sociological. This gets back to the ego issue. If you've got your fellow programmers and so on reviewing your code or your design, there is a natural. We as coders tend to be very protective of our code. Jerry Weinberg, all the way back, 1971, Psychology of Computer Programming, tried to push an idea which he called egoless programming, which is like we should have no emotional attachment to our code. And that's the only way we can get the reviews necessary to get the true analysis. And I agree with his arguments, but the simple truth is we're very attached to our code. and often in reviews, there's a fine line between here's a problem I see with the code, or gee, I would have done that differently. One is often a matter of taste, and the other one is a matter of, oh, this code isn't working correctly, or here are the problems I see. It is good for code reviews not to have non-technical managers there, not to have unprepared engineers there, and have the person leading the review be someone other than the person who wrote the code. Okay, look at that. You guys have a full hour. Put in your 7 hours. Actually, I said that last time. I still haven't gone back to review any revisions you've made to your project deliverables. So got another week to get that done, and I'll go through and give you final grades on all your deliverables, except of course the videos, which are the last day of class. Read 3 through 6. He talks about maintenance, but boy, this was just getting too long. We'll talk about his maintenance stuff out of chapter 2, and we'll talk about chapters 3 through 6, which are actually all quite short. The Webster readings, Webster 6, I'm deferring to next week too, because that actually ties closely with maintenance. Podcast, and then next week we will review the readings, and then we'll review for the midterm, and we'll do the midterm in 2 weeks. Any questions? Yes?
Will that finish the book?
That will finish the book.
It just has 6 chapters. Okay.
So you'll be done with the book, you'll be done with all the Webster readings except for the pitfalls. You don't have to read pitfalls until after the midterm, but as I said, you probably want to go look at them at the very least. And the link will take you to a page that will simply list the titles of all the pitfalls, because those may come in very handy on the midterm. So that's worth at least being familiar, knowing where the link is, looking at a few of them and so on. And then, in fact, let me, hang on a second here. Look at my schedule. Put glasses on to read this. Okay. I just want to see what's there. Make sure I'm sure of the schedule. Okay. So next week is review the midterm. And I said after the midterm, start reading Webster 7. So I should actually slip that down to Monday 13th. Monday the 13th is midterm. Then I have you reading Webster 7, and I'll probably slip the due date on that so that you're not worried about it over Thanksgiving. So we have the midterm. The 20th, we will discuss midterm results. And that's probably all we're going to do on the 20th. You'll have no assignments for the week. Don't have to do billable hours for the week. Just enjoy Thanksgiving. And then the following Monday, we've got a few more lectures. I'll probably look on the 27th or the 4th at possibly having my daughter Chris come in to talk about life in the real world. And especially now that she's been through what was one of the big questions she had last semester and she had no answer for, which is negotiating salary when you're already in a job. She actually has gone through that and went through it successfully. So we'll just have, those will be fairly light, the 20th and the 27th. One of them will probably be Chris, one of them will probably be going through the pitfalls. We'll have the final project presentations on the 11th, and then the final exam is optional, will only be for people who want to pull up their grades for one reason or another. And as I think Matthew raised the first day of class, it won't hurt you. It'll be purely extra credit, so it's not like, oh, we're going to average your midterm and your final. It'll be a relatively short final, but it'll be a chance to sort of take another whack at the types of problems that were on the midterm. Any questions? Anything? If not, guys, I'll get out of here early.